everybody. Welcome back from the poster sessions. I hope you enjoyed them. And we're about to start our industry and sponsor event. And first, I would very much like to thank our sponsors for supporting the conference, for helping us make this possible as it is now. And first in line for today's sponsorship presentation is Qualcomm. And I believe Gabriele Cesar will be presenting. And I'm looking forward very much to your presentation. And the stage is yours.
A lot. 1 second. Can you see my screen?
It's not full screen yet, but we can see it. There we go.
Okay, great. Hello, everyone. I'm Gabriele Cesar, a PhD student from Qualcomm AI Research in Amsterdam. And I'm going to talk about on-device group equivariance CNN for medical imaging. This was a project we did last year with Mirgani, Taco, and Max, my co-authors. And that ended up in a demo we presented at NeurIPS. The idea behind this project was initially, this project was initially motivated by the idea that deep learning solutions can be combined with mobile devices to reach a larger body of patients and provide high quality medical diagnosis as like in regions of the world where skilled technicians are less available. This is nice, but deploying like deep learning solutions on mobile devices often like introduces a number of challenges related to power consumption, computational efficiency, and memory efficiency. Additionally, in medical imaging, the labeled data is often like expensive to gather, so it's not as available as we will need to train like big deep learning models. On the other hand, medical images often present certain symmetries, such as rotational symmetries. For example, if we have like a tissue scan, this tissue doesn't have a preferred orientation, and we would like the prediction of our model to be consistent at any possible rotation of this tissue. It would be nice then to build a model which is able to generalize over a rotated version of this model, of this image, by only seeing one of them, since they are ideally equivalent. This is exactly the idea behind equivariance. In our demo, we developed an efficient equivariant neural network, which we trained on a medical imaging task, and we deployed it on a commercially available smartphone to perform segmentation in real time from running on the smartphone. Before going a bit more in detail into the demo, I want to spend a few words on equivariance. I think that most of you are already familiar with the convolutional neural network, and you may have heard that they are translation equivariant. What does this mean? If you imagine that you train like a segmentation model using a convolutional neural network, you will have that if you translate the input of this model, you will produce a translated segmentation mask. This is what we see on the left here. This is a nice property, but conventional convolutional neural network are not equivalent to other transformations, such as rotations. We can see a nicer example here. On the top row, we feed rotated copies of the same image inside the convolutional neural network, and what we see in the center here is the output produced by the network. It's clear that the output is not perfectly rotating, but it's deforming and transforming unpredictably. Fortunately, the literature on equivariant neural network, and in particular rotation equivariant neural network, is quite rich, and now we know how to build rotation equivariant convolutional networks. And by doing so, we are able to build which are exactly the desirable property we want. So if we feed rotated versions of the same image, we produce a rotated version of the same output. This is, again, quite a desirable property when working with tissues, for example, scans of tissues. How do we achieve rotation equivariance? The main idea is generalizing the concept of convolution beyond just translations, but also to applying rotations of the filters. To be able to deploy our neural network models on device, we rely on quantization to improve their cost, the computational cost, and their power consumption. The idea is that rather than running our models using floating point values, we represent their activations and their weights using only 8 bits. This allows for faster computations and less power consumption, since we rely on the more efficient integer arithmetic in hardware. But this is at the cost of introducing noise in the activations and the weights of the model. This unfortunately can reduce the overall performance. So we need to use techniques like the data-free quantization techniques from Nagel et al. To renormalize the weights of the network to basically make it more robust to the quantization noise. In our demo, we relied on efficient architecture based on DeepLab v3 with a mobile Gen2 backbone. We trained our models on histopathological scans of lymph node sections, which were extracted from the Chameleon dataset. All our equivalent model is implemented using the PyTorch library e2cnn, while the quantization is done through the AI model efficiency toolkit developed by Qualcomm. So we can now have a look at the demo. In our demo, we see like a model running in real time on a commercially available device. And the task is that of classifying each pixel in a tissue scan as either benign or malignant. In the visualization, we show 3 colored masks, which represent the prediction of our model. The green represents the true positive, the yellow represents the false positive, and the red represents the false negative. So a perfect prediction should only include green pixels and no yellow and red pixels. Because tissue doesn't have a preferred orientation, we feed the rotated copies of the same of each scan in the network to observe how the prediction change. For comparison, we show also an equivalent conventional neural network running on the device and processing the same inputs. On the left, we show the prediction as the input is rotating, while on the right, for better visualization, we show stabilized version of the frame rendered on the left. It's evident that the prediction made by the conventional neural network are not really stable to rotations. We see that the mask in output is not consistent at each rotation, but it's rather changing and deforming. On the other hand, the prediction made by the equivalent neural network is much more stable to rotation and therefore more robust This also leads in the end to an overall improved accuracy. Finally, we have a look at some quantitative results. In these 2 plots, we show the accuracy and the intersection of error scores for both the equivariant and the conventional neural networks. The full lines show the models running with the full precision arithmetic, so with float values, while the dashed lines show the models after quantization. The red line is the equivariant network, the blue one is the conventional one. We first observed that the equivariant network is always outperforming the conventional one. Both plots show the performance at each rotation of the test set. So in this plot, it's evident also that the equivariant network is much more stable to rotation. We see, for example, on the left plot that the accuracy is consistent for each rotation of the test set. Conversely, the performance of the conventional network depends on the particular angle at which we rotate the test set. Finally, comparing the performance before and after quantization, we see that the quantization techniques we used are able to retain almost completely the accuracy and the intersection of reunion of both the equivariant and the conventional models. Additionally, the quantization does not reduce the stability of the equivariant model, and we see that the model is still quite consistent over all the rotations of the test set. This was my presentation. Thanks a lot for your attention, and let me know if you have any question.
Video bitte hier. Thank you very much, Gabriele, for your interesting presentation. We do have a little bit of time, so if there's a question or two maybe from the audience, we could do that. Is there someone who wants to ask a question? Then please raise your hand and you will be elevated to the stage. And while we're waiting for that, I have one question. You said that the quantization resulted in a slight loss of accuracy. I saw that on your last plot. But interestingly, the conventional network seems to be a little bit better after quantization, at least in terms of accuracy. Is there a reason for that?
Yeah, I mean, it's I mean, accurate, like quantization in general introduces some noise, right, in a neural network, which is not necessarily like this. Quantization is not pure quantization. We didn't take the floating points and convert it to int, but we also applied these techniques that should renormalize the weights and make the network more stable to quantization. Most of the times, the loss in accuracy and performance is quite low, but sometimes this can also act as some kind of, you can imagine it as a regularization, which make the model a bit more, performing slightly better. Also considering that this dataset, like the price, like these are segmentation dataset, so like you don't have either an image with all malignant pixels or all benign pixel, and it could be that this quantization makes the model slightly more biased toward maybe the benign class, which is more frequent and slightly improves the performance.
All right. Okay. Thank you very much. I don't see any further questions in the chat. So if you have any questions, I would suggest you run up to the Qualcomm booth, which is located in the lobby. And again, thank you very much for supporting us. And we can move on, I guess, to the next presentation, which is by Kristen Petersen from HeartFlow. So the stage is all yours.
Can you see my screen?
Oh, no, sorry, not Kristen, Karsten. My apologies. I didn't memorize the name properly.
No worries. Well, actually, greetings to Lübeck. I'm from Plön, so it's very close by. So my name is Karsten Petersen. I'm a staff research scientist at HeartFlow. Have been working there for roughly 7 years, mostly focusing on medical image analysis and machine learning. And I would like to give you a small overview of HeartFlow. HeartFlow has been founded roughly 10 years ago at Stanford by 2 professors, one for cardiovascular disease and one for mechanical engineering, and has since grown to a full-fledged companies of roughly 400 employees that are mostly situated in Silicon Valley and Austin, Texas. We also have some satellite offices in other areas outside of the US. And HeartFlow is mostly dedicated towards helping physicians improving the diagnosis, prognosis, and treatment of coronary artery disease. So coronary artery disease, as you probably know, is caused by a buildup of plaque in the coronary arteries. You can see that especially here on the right in this image where you see this tightening, the stenosis. And if this blockage of the blood is very severe, then we call this obstructive disease. So not enough oxygen-rich blood can reach the heart to make it pump. And in that case, so if it's obstructive, then the patient needs to be treated either with a stent, which is a metallic coil that needs to be inserted into the coronary artery, or it needs to be bypassed, for instance, with a blood vessel from the leg. However, if it's non-obstructive, so if the disease is mild, then the patient can either be treated with lifestyle changes or medication. Coronary artery disease is very common. Cardiovascular disease, which is an umbrella term, so it includes coronary artery disease, stroke, and peripheral artery disease, actually accounts for every 3rd death in the Western world, and roughly 650,000 people in the US alone have died from a fatal heart attack per year. So that is nearly similar to what COVID has reached. And more than $200 billion has been spent in the US alone on improving the diagnosis and treatment of patients with coronary artery disease. So if we look at the typical pathway for a patient that enters the hospital with symptoms of coronary artery disease and is stable, then typically you run a suite of non-invasive tests. So this can be, for instance, stress testing where you run on a treadmill, or EKG, nuclear tests, or CT angiography. And one of these tests might not be sufficient. The accuracy is not very high. There are a lot of false positives and false negatives. So you might run several of these tests to come to a conclusion. Unfortunately, these tests can be contradictory. And so in many cases, the physician wants to err on the side of caution, wants to be very cautious, and sends the patient to the cath lab. And in the cath lab, a catheter is inserted, and typically an invasive coronary angiogram is taken to come up with the ultimate conclusion if the disease is obstructive or non-obstructive. And it turns out that roughly two out of three patients in the cath lab don't need to be there. They could be treated with medication or lifestyle changes because the disease is non-obstructive, but it's first detected in the cath lab. And yeah, cath labs are very costly, and invasive coronary angiogram can also be risky to the patient. You might, for instance, perforate the coronary artery. So HeartFlow's mission is really to offer an alternative. We just rely on a typical CT angiogram, and then we simulate the blood flow in the coronary arteries to make a decision if the disease is obstructive or non-obstructive. So we offer both anatomical and physiological information. And this looks in a bit more detail as follows. So physicians around the world send CT images up to our cloud. There we run a suite of algorithms to extract the coronary arteries. And these coronary arteries are typically edited by human experts to obtain a very accurate delineation of the lumen, the inner wall of the artery. As the next step, we then construct a physiological model, which defines assumptions about the inlets and outlets. So, for instance, the size of the myocardium tells us the amount of total blood in the heart, and then we have assumptions on the viscosity of blood and several other physiological assumptions. So these are relying on principles of physics, basically. So with the anatomical model as our domain and the physiological model to define boundary conditions, we have all the ingredients to set up a system of partial differential equations, which we can solve for pressure and velocity. This basically solves the Navier-Stokes equations. And with that, we get this color-coded coronary artery tree, where blue indicates that the pressure is very similar to the pressure in the aorta, and red indicates that we are getting towards obstructive disease. So you can see exactly the location where we need to intervene. This is basically a similar depiction of what I just explained. So the CT image is sent to the cloud, where we run our machine learning algorithms together with human experts that correct the solution where needed. Then there's the physiological model, and the output of this entire process is a PDF file that summarizes the most important measurements, or an interactive model in an app on an iPhone or an iPad. And this test works really well. So we have published many papers on this. The references are given in the end. Essentially, most of the angiograms, unnecessary angiograms, can be canceled. And the cost saving, as you can see, is also immense. We also have regulatory approval for our technology, of course. So 10 years ago, we got the CE mark. 7 years ago, FDA approval and PMDA approval in Japan in 2017. Similarly important, our technology is reimbursed in many geographies. 96% of the people in the US have insurance coverage. And this test is really applied in practice. So we have already treated we have already applied our technology to more than 75,000 patients worldwide. And especially a lot of the leading hospitals in the world have adopted this technology. So we are a very research-minded company as well. We have published more than 400 papers with a company of roughly 400 employees. We also have more than 400 patents to express our ideas, and we have run many clinical trials. I don't know exactly the number. I think it's at least 16 at the moment. So if you look at the landscape for diagnosis, prognosis, and treatment planning, then there are multiple different technologies that can be used for instance, assessing the plaque characterization, the degree of stenosis, the functional significance, or the perfusion. FFRCT is basically synonymous with heart flow analysis, so that's our product. There's actually a real test called fractional flow reserve, which we mimic. So there, a catheter is inserted into the coronary artery with a small pressure sensor at the tip to measure the blood flow, and that's basically our ground truth. But you can see it's a very heterogeneous landscape. So our idea, what we're currently working on, is to replace all of these tests with CT plus heart flow. So we want to provide information about the plaques, the stenosis, the physiology, and the perfusion that can be used for diagnosis, prognosis, and treatment planning. And if we then look at our current portfolio, we basically have products for expressing the stenosis degree, the functional significance, the perfusion, the plaque characterization, but we also, you can find that on our homepage, have the ability with our virtual model to do interventional planning. So we can, for instance, simulate what happens if you set a stent inside the coronary artery. How does it affect the functional significance of that blockage? And if we go even one step further, so if we look ahead what we could do, there are of course other organs in the body that we could address, like the brain or the peripheries. We have basically patented blood flow simulations for the entire body, and there are many other coronary applications that we can look at. So if this sounds exciting to you, then please reach out to us. We'd love to hear from you. We have some open positions that you can find on our homepage. As I said, we are focused on fluid simulation, medical image analysis, machine learning, deep learning. Our headquarters are in California, Silicon Valley, and we also work very tightly together with Ben Glocker's lab at Imperial College. So we have a couple of PhD students and also researchers there. And with that, here are some references. I would like to thank you very much.
Thank you. Thank you very much for the really interesting presentation. If there are any questions from the audience, I think we can take one or two. And while we're waiting for them, I do have one question as well. You were talking about a human in the loop in the AI process of detecting the stenosis, the plaques, and so forth. Could you elaborate a little bit? Because this seems to be, at least to me, a bottleneck in your process of processing things in the cloud. So that could take a while, right? If
Yeah,
someone can work on this.
Yeah, that's a very, very good question. So our approach is to always assure the highest degree of quality. We could, of course, just run our algorithms and on average, they reach human level performance, but there are always outliers in every segmentation algorithm because these examples may not be reflected in the training data. So to ensure that we don't send out unreliable results similar to like a self-driving car or so, we need to check with the human experts that these results are correct. So our mission is basically to always ensure the highest level of accuracy and then improving the speed where we can, but we need to be very sure that we can.
I see. Okay, thank you. I can't see any questions, so I would like to encourage all the participants to walk up to HeartFlow's booth in the lobby and talk to the people there, ask them any questions you might have. And thank you very much again for supporting the conference. And I wish you a pleasant evening. So we can switch over to the next presentation in line, which is by Alishan Bozkurt. I hope I pronounced this slightly all right. And the stage is
That was
yours.
excellent, actually.
Great. So that's a presentation by Page AI, and I'm looking forward to hearing what you have to say. Thank you.
Thank you. Alrighty. Perfect. All right. Greetings from New York. I am Alican Bozkurt. I am an AI scientist working at Page AI. I am working on the breast clinical team, and our team basically develops clinical solutions to help pathologists detect like breast cancer. And today I will be talking about like using machine learning to classify lesions in breast pathology. And obviously, like I'm an employer of Page AI. All right, I would like to start with our mission. Our mission is basically to empower pathologists, clinicians, and researchers to make accurate diagnosis and treatment decisions even faster by unlocking insights and information from the tissue. Now, one question that we can ask here is basically, do pathologists need empowering? And turns out the answer is yes. When we are looking at like the historical data, it seems that the number of pathology cases in the United States and Canada, and actually like throughout the world, is actually increasing, but the number of pathologists are decreasing. So this is a problem for general pathology. In breast, this is clearly an issue. The reason being like due to the routine screening, the breast specimens are high in volume, and breast resection specimens take a lot of time to analyze due to like the number of glass slides and the over of tissue area for like the review. So basically, we have fewer number of breast pathologists, and we have like a lot of breast pathology slides, and it takes a lot of time to analyze those slides. And machine learning obviously has been shown to improve the efficiency and the accuracy of cancer detection in like a variety of tissue types, and we are basically hoping to apply this into breast pathology as well. Right. So I would like to talk to you about like a little bit about the breast pathology here. So what you can see here, like the breast pathology includes a spectrum of benign, like atypical, pre-invasive and invasive lesions. And the things that we are interested here is these two things called like lobular and ductal carcinomas and hyperplasias. So these basically go from like less severe to more severe as like the atypical hyperplasias, carcinomas in situ, and invasive carcinomas. And basically these have like two different flavors, like ductal hyperplasias and carcinomas and lobular hyperplasias and carcinomas. And obviously this diagnosis changes the treatment and the outcome. So it is actually crucial for the pathologist to basically go through this analysis. And diagnosis random on these kind of biopsies have actually like a relatively high discordance rate, especially without like an expert second review. And as I mentioned, like this analysis needs to be done for like the appropriate patient management, right? And so our aim for this basically model would be to basically classify a breast slide into these like 5 categories, like the LAH, LCAS, ADH, DCIS, and invasive, right? So for those of you who doesn't know like how those slides are basically created, the idea is basically, and I do apologize for the graphic nature of this image. So basically, once a biopsy is cut out of the patient, what you do is basically you divide it into like small parts, and you basically put into these like cassettes, embed like them into like paraffin blocks. Then you basically cut those paraffins and stain them. And if you're doing like digital pathology, you digitize the slides. And basically, depending on whether things are digital or not, the pathologist looks at the slides in a microscope or a computer screen and creates some reports for those slides. Now, one thing I would like to mention here is basically, obviously, pathologists do not create these reports per slide, because even if you have like a small amount of cancer, the patient has cancer, right? So basically, these reports are usually created over like not at the slide level, but the specimen level or like a case level. Right. So what is basically so hard about like computation pathology? Why can't we just throw whatever we know from like computer vision into this problem? The problem is basically scale. When we're looking at basically this computational, the digitized slides, the typical slide is basically around like 6 billion pixels. And basically compared to the toy data sets, if you will, that is used in like computer vision tasks, just like a routine example, like the whole CFAR10 data set basically fits into this small image onto like a single slide. And you can't really like downscale the images and try to process them, because the things that you are to find may still be like in a really small part of the image. So you actually need to go through all of this image in a relatively this scale. And one basically solution is to basically divide the image into tiles and process each tile separately. Right. So the other problem is basically coming from the ground truth. So how are you going to get the data, the labels to train your models? So one obvious solution is basically like pixel level annotations, but as we have seen, since the images are like too large, the exhaustive labeling is like simply prohibitively time consuming. And in addition, since like the pathologists are actually not trained in this task, we have seen like a lot of inter-reader variability in those annotations. But one other thing that you can do is basically try to leverage the fact that the pathology workflow that we have seen in previous slides already creates an output, right? In form of like these reports. And what you can do is simply mine those reports to extract the labels that you care about. And this is basically how, what we are going to do for this work. Right. So one problem that I mentioned is basically these reports are usually not, so our like model takes in like a tile which is like a really small part, like a 224 by 224 part of that slide. But our ground truth tables, as we have seen, are not at that level. It's like on a much higher level. So what we can do is basically something called like multiple instance learning. So we're going to treat all of those images as a bag of instances, or in this term, like tiles. And we will we will try to classify the bags instead of like the tiles itself in terms of like supervision. And a bag will be positive if at least one tile in the bag is positive. So given that whole large image, even if there's like a small bit of cancer in there, so we are basically gonna treat the whole slide as a cancer. And basically, if there are simply no like cancers, then it will be just benign, right? So this method will basically work perfectly for like a needle in a haystack kind of problems. And the way basically this algorithm works is once we basically divide the images into tiles, we're gonna identify the backgrounds and we're gonna simply omit them. Then we're gonna run inference over all of the tiles in our data set. Then we're gonna rank them according to the probabilities, and we're gonna only backpropagate over the like top some number of tiles. This can be seen like an implicit form of like hard negative mining, actually. Yep. And so using this method, we basically trained and validated like a SE ResNet 50 on like a 13,500 like specimens. And this basically corresponds to like almost like 5,400 54,000 slides, I'm sorry. And looking at like this, dividing into tiles, this corresponds to like 800 million tiles. And if you think about like, again, the toy examples in the computer vision literature, one epoch over this data set would correspond to basically like 800 epochs over like a ImageNet. Right. So, well, this is actually one of the harder problems. So it's not only like a problem in terms of like science, you need to figure out things that you need to extract those labels and do the model development, but this is like a hard engineering task as well. Right. So we basically trained and validated this model, and these basically how the ROC curves look like. And without like any reference, these are kind of meaningless. So we went and checked and found this like paper by like John L. Moore et al. That has conducted a story with like study like a 115 pathologists. And we are basically comparing here the pathologist specificity and sensitivity from that paper and what is paged like this model sensitivity at the pathologist specificity. And as you can see here, we have been like doing better in like ATPS, LCAS, and DCAS, and we are doing only slightly worse in invasive category. This is like a crude check, but it basically provides us like a baseline. So in conclusion, basically, we created like a high performance model that can classify breast lesions into like invasive carcinomas, DCAS, LCAS, ADH, and LAH. We have been like ongoing work about like adding more labels in something like a grading of the lesions, detection of like the non-atypical high-risk lesions and calcifications. And obviously, like we are trying to assess the generalizability of our model using like an independent real-world data. And obviously, with like all of the work that we are doing, this tool we believe has the potential to provide like increased efficiency and the accuracy to histological examination of the breast tissue. All right, so if you are basically interested in like the work that we have done here, we are hiring like AI scientists and AI engineers across not only for like our breast clinical team, but across like all of our teams and page. And if you're interested, please check out our like careers page or like send me an email at like my first name, last name at Page AI. Thank you.
Thank you very much. Thank you very much for the really interesting presentation. And also thank you very much to Paige for supporting MIDL 2021. Are there any questions from the audience? And if you have something, post it to the chat. Otherwise, I have a question in the meantime. You are tiling these slides into little pieces to make the AI algorithm work. And
Yep.
I was wondering, is it a danger that something that should be detected is by chance lying on the exact slicing position, so that something that would be interesting and would be detected by a human pathologist gets sliced in two and might not be picked up by your AI algorithm? Is this
Definitely. This was a concern, obviously. Yeah. So when we are doing the tiling, we are not doing we are overlapping the tiles to basically alleviate the problem as much as we can.
Okay, I see. There's a question in the chat. Someone,
Yes.
Michael Tardy, is asking whether breast cancer is the only type of cancer you're working on.
No, we are not. Our actually the flagship product is like prostate cancer. So we are also working on breast, and we are also in working multiple other tissue types.
Okay. Well then, thank you very much again for the really interesting presentation. Everybody should be encouraged to walk up to Paige's booth in the lobby. And we're looking forward to hearing more about these types of research in the future. So thank you again. The final sponsor today is the University Hospital of Schleswig-Holstein, but they figured it might not be necessary to actually give a presentation. They rather have prepared a set of little videos they wanted to share with you. And I encourage you to watch through them. The first one is really relevant to today's pandemic situation. And afterwards, Yanis and Alessa will come here and give you a little introduction to our social event tonight. So it is really worth your time. Stay on the call, on the video call until the end of the presentations. So can now together look at the videos from the University Hospital Schleswig-Holstein.
Jerusalema ikhaya lami ilondoloze uhambe nami zungangishilana Jerusalema ikhaya lami ilondoloze uhambe nami zungangishilana dawo yami ayikholana buso wami awukholana ilondoloze zuhambe nami dawo yami ayikholana buso wami awukholana ilondoloze dawo yami ayikholana buso wami awukholana ilondoloze zuhambe nami dawo yami ayikholana buso wami awukholana ilondoloze Jerusalema ikhaya lami ilondoloze ayikholana buso wami awukholana ilondoloze suhambe nami
Der Campus Kiel ist gespickt mit Innovationen und digitalen Neuerungen. Für die Patienten stehen ab sofort neue Services zur Verfügung. Etwa das webbasierte UKSH-Portal, in dem behandlungsspezifische Informationen abgerufen werden können, ganz bequem von zu Hause aus. An den Self-Check-In-Terminals können sich die Patienten von nun an schneller anmelden. Der Fast-Track zum Arzttermin. Unterwegs auf dem Campus? Kein Problem. Das Wegeleitsystem verschafft den Überblick und steuert zielstrebig zur Behandlung. Die Digitalisierung setzt sich im Krankenzimmer fort. Hier haben die Patienten Zugriff auf TV, Internet, Spiele oder die UKSH-Mediathek. Klinisches Personal wird durch Bedside-Terminals bei der mobilen Visite unterstützt, um Befunde abzurufen und die Behandlung mit dem Patienten abzusprechen. Ein weiteres Novum gibt es auch in der Klinikapotheke, die modernste in ganz Deutschland. Hier werden die Medizinprodukte in Reinräumen der höchsten Kategorie mit der Hilfe von Robotertechnologie aufbereitet. Bereits im Betrieb ist auch das Unit-Dose-System. Es garantiert, dass alle Arzneimittel von der Klinikapotheke patientenindividuell zusammengestellt, verpackt und direkt an die Stationen geliefert werden. Die Aufbereitungseinheit für die Medizinprodukte wird mit vollautomatischem Lager und robotischer Logistik ausgestattet. Außerhalb Dänemarks ist das weltweit einzigartig. In den OP-Sälen wird in Zukunft mit virtuellen Bilddaten operiert. Die Augmented Reality-Technik erleichtert den Ärzten die Orientierung durch den Körper und macht die Eingriffe noch präziser. Und mit den beiden Ideenschmieden Innovation Hub und Healthcare Hackathon wird die Technologie der Medizin von morgen mitgestaltet und deren Chancen genutzt. Hier werden Visionen Wirklichkeit. Die Zukunft ist, was morgen kommt. Der neue Campus des UKSH ist dafür gebaut.
Ein solcher Hybrid-OP ist einerseits ein voll ausgestatteter Operationssaal, aber gleichzeitig auch ein Katheterlabor. Und da kann man also minimalinvasive Eingriffe machen an den Herzklappen, aber hat gleichzeitig die Sicherheit, dass zum Beispiel ein Herzchirurg auch jederzeit eine offene Operation vornehmen kann. Der Aufwand für einen solchen Hybrid-OP, sowohl von der Technik her wie auch übrigens vom Personal, ist sehr hoch, dass das eben nur sinnvoll ist, das in großen Krankenhäusern und insbesondere Universitätskliniken durchzuführen.
Also wir sind als UKSH natürlich unheimlich groß, als zweitgrößtes Universitätsklinikum in Deutschland. Wir bilden damit eine große kritische Masse, alleine schon hier im Standort in Kiel mit 1200 Betten, mit den Möglichkeiten, die uns der Neubau eben schafft und ganz jetzt herausgenommen eben dieser Hybrid-OP, wo wir eben ganz toll nicht nur Patienten auf allerhöchstem Niveau als Maximalversorger behandeln können, sondern der auch alle Möglichkeiten bietet, Verfahren wissenschaftlich weiterzuentwickeln und auch wissenschaftlichen und ärztlichen Nachwuchs ausbilden können.
Das eignet sich besonders für Patienten, die beispielsweise eine höhere Blutungsgefahr haben oder auch für Patienten, die Angst vor einer OP haben mit tiefer Hirnstimulation. Und das ist mit einem geringeren Risiko für Komplikationen behaftet. Und das ist eben das Tolle, man kann das Zittern deutlich reduzieren, um ca. 90%, ohne dass man die entsprechenden Risiken hat, wie sie beispielsweise bei der tiefen Hirnstimulation vorliegen.
Wir heizen erstmal das Gewebe so bis ca. 45 Grad auf, gucken dann, ob wir uns am richtigen Punkt befinden. Das heißt, wir haben bei diesem Patienten gesehen, dass sich das Zittern deutlich verbessert hat und dass wir keine Nebenwirkungen hatten. Das heißt, es ist nicht zum Auftreten von Sprachstörungen zum Beispiel gekommen oder einer Koordinationsstörung, was für uns bestätigt hat, dass wir an der richtigen Stelle sind. Das ist natürlich mit so einer Technologie, die doch recht neu ist, die extrem fortschrittlich ist, die ist sicherlich in einem universitären Setting, wie wir es hier haben, sicherlich sehr, sehr gut aufgehoben.
Hi, welcome back, and once again thanks to all our sponsors who made this event possible. And yeah, it's time we made it through the first the first live interaction time and the first live discussions, all these presentations, all the panel discussions, all the poster sessions. We hope you had great discussions, we hope you had great interaction, and now of course we are not done because we promise you social events, and there we are. It's time for the first get together, and as you might have already noticed, the roof terrace is already opened. If you go to the to our main lobby, you might find the one or the other red arrow, which are actually a lot of them. So you shouldn't have any problems to find the access. There are 2 accesses at the downside of the lobby. So please go there and enjoy your evening. And of course, it's not just a roof terrace. We promise you barkeepers, and we have barkeepers. So now is the time to get your favorite ingredient for your favorite cocktail that you hopefully already shopped, and maybe also for the MIDL Mule, our new signature cocktail. If you didn't go shopping, don't worry. Go to the bars anyway. We already said that the barkeepers are very good and flexible, and they can improvise with basically everything you can find in your own kitchen. So just go to them and they will make you somehow a drink from anything. And so yeah, grab your colleagues, grab your friends, have some nice discussions and nice chats on our roof terrace, and as we already mentioned, maybe you can even take a first glimpse on the old city center of Lübeck.
So, time for our first cocktail, right, Janis?
Cheers!
Cheers! See you at the bars!